Hi, I'm Matsushika Kogawa from Ritsumeikan University, Japan. I'm going to talk about vertical bend and T-branch travels of an articulated wheeled in-pipe inspection robot by combining its joint angle and torque controls. Aging of pipeline facilities in urban areas grow into a serious problem. To prevent these accidents, pipeline inspections and identification of deterioration points in advance is of great importance. However, manual inspection is time-consuming and costly because general pipelines are thin and installed underground or in high places. Therefore, robotic in-pipe inspections with cameras and thickness measurement sensors have been attracting attention. Although a number of in-pipe inspection robots have been reported, the major challenge is to pass through bend and T-branch pipes, including vertical and horizontal sections with inner diameter of 4 inches or less. To pass through such a long and narrow pipelines, a snake-like structure is considered to be suitable, and thus numerous studies related to this have already been reported, such as a robot with a body that resembles a real animal snake, earthworm-like peristaltic mechanism, and a robot that combines a snake-like structure with active wheel drive. However, even these existing in-pipe robots still have problems such as slow adaptation speed to T-branches, short travel distance. In response to this, we have established the following requirements for the development of practical in-pipe inspection robots. Adaptive inner diameter of pipes should be 4 inches and less. The robot should be equipped with the mechanism to push the drive wheels against the inner wall of pipes and can pull the cable over a long distance without the slippage of the wheel. The robot should pass through T-branches in all directions at a fast speed, both horizontal and vertical. Our goal is within 10 seconds. To achieve these goals, we propose an articulated wheeled in-pipe robot called IROS 5.2, which is an improved version of our previously developed robot, IROS 5.1. The robot is composed of only a single active compliant middle joint, 2 passive compliant joints, 3 drive wheels, and 2 roll wheels. T-branch travels are achieved by controlling both the joint angle and the torque. However, IROS 5.1, former version, have a problem with the wiring inside the middle joint, which was prone to disconnection, and there was no verification of the travel performance to the T-branch in any direction, including horizontal and vertical. Therefore, this presentation will discuss these points. This is a mechanical overview of the robot. Omni wheel with NBR, nitryltadiene rubber, is specially designed to achieve durability and high friction. Spherical wheels at the head and tail of the robot are made of silicon casted by handmade. For joint torque control, the polyurethane-based series elastic actuator, SEA, is installed in the middle joint. The position of the angle sensor in the new design is different from the former one, although there is no difference in the placement of potentiometer 1. However, in the former design, potentiometer 2 revolutes around the middle joint axis, while in the new design, potentiometer 2 does not. In principle, angle and torque control of the middle joint is possible in both cases. However, in practice, there is a trade-off relationship between the wiring problem and the control point of view. For example, in the former design, only a single angle sensor is required for torque measurement. However, since the control board is located near the joint motor, the power and signal lines for the potentiometer 2 must be routed inside the middle joint. In the new design, the potentiometer 1 and 2 are placed very close to each other. Thus, all the wiring can be placed near the control board. The middle joint angle can be acquired from only a single potentiometer, which improves the accuracy of the angle control. However, because of the use of 2 potentiometers for torque control, joint torque of the new design is less accurate than that of the former design. Here is the difference between angle control and torque control of the middle joint. In continuous pipelines that contains only straight or winding pipes, that robot can automatically adapt to the different pipe environment by controlling the torque of its joints and pushing its wheel against the inner wall with the same force. On the other hand, when the path is branched, the robot must turn or part of its body toward the next path. Therefore, it is necessary to move the wheels away from the wall using angle control and then press the wheels against the wall again when the part of the robot body enters the next path. Prior to the experiments on the T-branch, travel performance in bend pipes using only joint torque control were examined in two 4-inch pipelines, one horizontal and another vertical, jointed by 3 bend pipes and 4 straight pipes. The robot passed through all pipes very smoothly without getting stuck at all. This is because the joint torque control was working well, and the Omni wheels were firmly pressed against the inner wall of the pipe, and thus the slippage can be avoided. Graph showed the measured angle and torque of the middle joint during the experiment. It can be seen that the joint torque is correctly controlled despite the influence of the noise. When entering the bend section, the joint bend passively under the joint torque control alone, which means that the joint is adapting to the environment without any problem. With only the angle control, the robot cannot maintain contact with the bend pipe and cannot obtain enough force due to the low normal force from the pipe wall. In the previous design, T-branch travel in any direction was achieved by giving the cosine curve trajectory as a target angle to the middle joint. However, it took a long time to pass through the T-branch due to wheel slippage. In this study, therefore, parameters for the cosine trajectory were tuned to verify the travel performance in the T-branches. Here is how the robot travels through the T-branch. First, the torque of the middle joint is controlled in the straight pipe. Joint torque was set to 1.0 Newton meter to press the drive wheels against the inner wall of the pipe. Then the robot moves forward. When the head of the robot enters the T-branch, the signal to switch from the torque control to the angle control is commanded. After passing through the T-branch, the robot automatically returns to the torque control after one cycle of the cosine trajectory of the target joint angle. Finally, it moves backward and passes through the T-branch again in the same way. This is the experimental result in T-branches in total of 10 patterns. You can see here the robot can pass through all T-branches very smoothly from A to J. The first thing to mention is that our new robot can pass through a 4-inch T-branch in all directions with almost 100% probability and within 10 seconds by switching the torque control and angle control. Also, the wiring of the new design did not break even after several hundred repeated experiments. In our previous experiments, about 40 degrees of amplitude A and 22 degrees of joint offset B were selected based on the kinematic analysis. In the present experiments, however, 35 degrees of amplitude A and 15 degrees of joint offset B were set. In this combination, the joint angle reached only up to 50 degrees, which is smaller than that in our previous work. As a result, the lead drive wheel is pressed against the wall with larger force. Then the slippage can be suppressed. On the other hand, in our previous experiments, the angular velocity omega of the cosine function was controlled at 0.9 radian per sec. However, in the present experiment, different value of omega was examined from 0.9 to 1.6 radian per sec. As a result, the success rate was highest at 1.6 radian per sec for all courses except E and F. However, it was highest at 1.2 radian per sec in those courses of E and F. This might be because the middle omni wheel leaves the inner wall of the pipe during the T-branch travel, unlike the trajectory proposed in our previous work. The dynamics was not taken into account, and thus it is better to drive the middle joint slightly faster than the value obtained by the model. That's it. Thank you very much.